Thank you very much for the introduction and for this great invitation and opportunity to come back to Lyon and enjoy the city, the sun, and of course this wonderful community of catalysis. I'm very happy that the electrocatalysis is now being more prominently featured in this conference. I will be talking about catalysts and the catalysts as dynamic materials. As you could see there, a catalyst is actually changing during the reaction. So we start with a pre-catalyst. It will go a certain activation. It will have some fluctuations. You have different initial phases of this material. If you are lucky, you come into a state what we call the frustrated phase transition. And in this state, this is going to be when your catalyst is at its best. If you're unlucky, you will go subsequently to a deactivation process. These are kinetic processes that are coupled, everything that happens to the catalyst, plus a second kinetic process, that is what happens to the reactants. And you see here that, of course, the reactants, you will have to take into consideration diffusion, activation, other conditions during the reaction, transport, etc. So to understand catalysis, you need to think about the following. You have repetitive chemical conversion, and this is also always coupled to a state of this dynamic interface structure. It's even more complicated because you want to have a stable productivity, and you want to have that the active mass is stable morphologically, but at the same time, you need to consider that the surface is going to be regenerating and creating these active sites. So this brings us a lot of problems, but also a lot of exciting science that can be done. I'm going to give you some example. This is here a very simple example of a ruthenium surface. And the video that you are going to see is water formation with image in a near ambient pressure low electron energy microscope. You see here that we are dosing oxygen and hydrogen, and you see water formation. And what is surprising is that this surface, that is a perfect single crystal prepared in ultra-high vacuum, is basically showing these dynamic changes. And that is very complex because it's not completely homogeneous, even though you are working with what should have been a perfect single crystal. To give you an idea about what I will be talking today, focusing on catalysts at electrodes, I will be describing that we can start with a pre-catalyst that might be very well defined. We are going to have a lot of information about what happens after the reaction. But if you really want to understand electrocatalysis or catalysis in general, you need to think about the working state of this catalyst. And this working state of the catalyst is going to be changing, and we need to be able to monitor this. As an example here, again, in the gas phase, before I go into the liquid phase, you see a copper surface. And these dots here, these are nickel particles. This is, again, a low-energy electron microscope video. And with very, very small amount of oxygen at a given temperature, you see that the steps of the copper surface, they are moving around. So my talk is called Beyond Static Models. Imagine everything that you are doing, considering that the surface is static, and I only need a minor amount of oxygen plus temperature that is typical during any catalytic reaction that we are looking at to induce these modifications of the surface. And of course, this is going to be adapting when you are changing also the reaction conditions. So I like to use this instance to give a quotation from Albert Einstein that everything should be made as simple as possible, but not simpler. So my talk today is going to go from the most simple system to the more complex, and you're going to see that from a single crystal, it's going to be a complexity. A single atom catalyst is not always going to be a single atom catalyst. So it's very, very important to do the characterization and to do the characterization as comprehensive as possible and under reaction conditions. For those of you from the thermocatalysis background, I like to choose this very, very fresh example to show you that many times we are trying to understand how a material works using ensemble averaging techniques. And so this will give us an average composition of the surface, an average oxidation state. But science is more complex than that. Here you see again a near ambient pressure, a low energy electron microscopy video, and you see a catalyst that is a copper catalyst, single crystal, with nickel particles. These are in dark, and we are here doing a reaction. We are doing the CO2 hydrogenation, so we are dosing CO2 and hydrogen. Here, these are the conditions. And you can see that there are different changes in the nanoparticles. Some of them disappear for the nickel nanoparticles. Some of them don't change much, the larger ones here. Some of them shrink during the reaction. So an ensemble average image of this, an ensemble average spectroscopy characterization is not going to tell us all of these details. And again, the complexity is there. With this type of microscopes, we can do microscopy and spectroscopy. So I can go locally and get information about my material with X-ray photoelectron spectroscopy and, for example, near-edge absorption spectroscopy. And I can see that certain areas here, for example, this is these areas. This is only copper. And then on the particles, I can identify this is nickel. And I can look at this also in the different environments and as a function of reaction time. And we are looking, in this case, nickel, and we are looking whether nickel is closer to the surface or more covered with copper. And this depends on whether you are dosing CO2 and hydrogen together or if you are also adding CO. When you add CO, we see that the nickel starts coming up, coming closer to the surface. So this is just a very, very recent data, but my idea is to show you that it's very important to look with microscopy and spectroscopy, ideally combined. If you can get a spatial resolution, this is even better, and that you can get this type of insight that I think is very much needed, how the material is reacting to your environment, and not only in a structure, but also in composition and also in this case, segregation phenomena and also alloying. So with this introduction, I'm moving to the electrocatalysis world. And one of the things I wanted to illustrate that many times we spend a lot of time synthesizing our precatalysts. In this case, I will show you an example from water splitting. And you see here thin films of cobalt oxide with two different surface orientations. These are prepared with epitaxial growth. So when we put these materials with two different orientations, our idea was to see if the initial structure of the precatalyst will affect electrocatalysis. And you can see here that, in fact, there is a change in the onset potential when we start with different precatalyst structure. However, this is not all. I'm going to show you that the active sites are also generated during the process. So when I'm changing the applied potential, I see that for this surface, the cobalt oxide 001, the structure is changing. And you see the formation of these small clusters, and this coincides with the formation of the active structure that is an oxyhydroxide layer. So we can image this as a function of the applied potential. For the other surface, there are much smaller changes. So we go to the same applied potentials, and you can see that there is some more roughening, but the changes are not as drastic. So this type of imaging, so in situ characterization with electrochemical atomic force microscopy, give us information about what are the sites that are being created under reaction conditions and how are these being modified as we are changing the applied potential. So only looking before the reaction and after the reaction is not going to show us these changes. And what is interesting is to know that the initial structure of the catalyst affects how it's going to change. So it matters whether you start with 001 or 111, but it's not true that it will not change, right? It is really very, very morphologically unstable. Now, the rest of my talk is going to be dealing with the electrocatalytic reduction of CO2. And for those of you who are not experts in this reaction, this is the perfect reaction to look at what is the role of the catalyst structure and composition, and also what is the role of the electrolyte in electrocatalysis. I'm going to focus today on the role of the catalyst structure. So we can go from CO2 with ideally renewable energy into making products such as ethylene or ethanol. And we want to avoid maybe making some other products. As I mentioned before, anything that you do to the structure of your catalyst is going to affect the performance. And I show you here an example. We synthesize a copper oxide catalyst for this reaction with initially a cubic shape, 100 facets. This was believed to be good for activating CC coupling and going into production of ethylene. And you see here a video acquired with a transmission electron microscope with a liquid cell. And you're going to see how my very nice initial catalysts, they are actually changing under reaction conditions. You see the formation of these dendrites. You see the splitting of these cubes. So whatever I synthesize is evolving under the reaction. And in this case, this is very strongly dependent on the reaction time. It's strongly dependent on the electrolyte. It depends on the support that you have underneath. So all of this needs to be considered. We have the possibility also now to create our material in situ and then to look at how this is evolving. I show you here, again, some images with low energy electron microscopy and also XPIM. So this microscope is at our beamline in Bessie. And I give you an example for a catalyst that is being used for the production of ethylene and ethanol from CO2 electrocatalytically. This is just an indication of what happens when you try to create this bimetallic catalyst. We have a copper surface, and we start evaporating silver. And what you see here is the growth of silver, so different coverages. And we can go from this clean surface to a surface alloyed with silver, and then we have a mix of silver plus this surface alloy. From these videos that I show you here, you can see that we can follow very nicely the growth, but as I mentioned before, we can also follow spectroscopically where is the silver here with respect to the copper. And we have at this beamline an electrochemical cell that we can attach to the beamline, and we can do, for now, quasi in situ, so we can do the electrochemistry and then transfer to this spectrum microscope without air exposure. And then we can look, for example, at where the silver is. Before the reaction in black, you see the silver to copper ratio is higher than the silver to copper ratio after the reaction. So we see that something is changing when we are doing the electrochemistry. We can follow how the morphology changed, but we can also follow where is the silver going, and we can get an information about this alloying that is happening there. So I told you that there is a lot of complexity, so I tried to start with the easiest thing, and you're going to tell me afterwards that probably it was much more complex than what I anticipated. So you see here a single atom catalyst. This will be typically used in electrocatalysis for CO2 electroreduction, also for ORR. And I'm going to be talking today about copper. And you have here copper bond to nitrogen, and then here we could have oxygen OH, so this is the typical, what we call metal NC catalyst. The preparation is not new. There is a lot of recipes in the literature. You start with this type of frame, then you put the metal precursor, you heat it at high temperature, and you get the metal incorporated in this carbon structure. And there are many different types of nitrogen functionalities there. You have pyridinic, pyrrolic. This is just an example of one of the possible, actually the most dominant one. We can do this and get single atom catalyst with copper, with nickel, with cobalt. And this will be my precursor. Now the question is the single atom really doing the catalysis? And if not, what is happening with these materials? And what can we do maybe to tune this? So we started with looking under potentiostatic conditions. So we have a constant applied potential, and we look at nickel NC catalyst, cobalt, and you see that mainly nickel is the best one at producing CO. This is the product that you get with this type of materials, with these metal NCs. And cobalt is also okay, but it makes more hydrogen, which we don't want to make. And if you look at copper, you see much less CO, you get more hydrogen. This is not what you want to get, but you start seeing some other products being made. Okay? Here we only change the applied potential, always constant applied potential. Now we thought maybe we can do something else with the copper. You can change the applied potential and have here at a very large negative potential, you start seeing other products being made. And then we are going to also be applying potential pulses, and we see that we can tune the selectivity. This is very nice because we have the same precursor precatalyst, in this case this copper NC, and then we apply potential pulses with a certain anodic pulse and the cathodic pulse, that is where we are doing the CO2 electroreduction. The cathodic pulse is the same for all of them, and we can see we get different products. Now what happened to the catalyst? If you only look at this material before and after reaction, you're going to see the material looks like this. It looks like highly dispersed copper. But it will be very strange that you can make with these single atom catalysts CC coupling processes that go beyond CO. So we know that this is not possible, and so we try to understand how did the structure of this single atom precatalyst change. So you can use X-ray absorption spectroscopy for this, and you see here the copper NC as prepared. It looks cationic as expected. Then during the reaction, you see this very large change. It looks more metallic. And then if you stop the reaction, remove the applied potential, it goes back to the initial state. So this after operando, it looks nearly exactly the same as they are prepared. So you have before characterization looks like single atom, after reaction characterization looks a single atom. During the reaction, it looks like particles were formed. This is that constant applied potential. And you can see it also in the extended X-ray absorption fine spectroscopy data. You can see here that the as-prepared catalyst looks more like an oxidic reference, and the under reaction conditions catalyst looks more like metallic copper. So the first information is that even at constant applied potential, your single atom catalysts are highly dynamic, and that this is a reversible system, which means that it adapts strongly to the reaction conditions, and that there is something that is changing there. So we start from these single atoms, we are making particles, and then it goes back. And this depends very strongly on three parameters. One is how strong is the metal-metal binding, in this case copper-copper binding, how strong is the copper absorbate binding, and for example, the interaction also with hydrogen that is being produced during the reaction, and then how strongly is the interaction of copper with the nitrogen anchoring sites within the carbon support. And remember that I'm working in an electrolyte, and here my electrolyte contains is potassium bicarbonate. So I'm going to have also some of this copper is going to be coming in the electrolyte, and then it's going to be dissolving and redepositing on the surface. We don't see loss of material. We can see this with ICP-MS, and we can see this also with X-ray absorption spectroscopy. Under potentiostatic conditions, you can see, as I mentioned before, you start with a cationic sample, then it goes into the formation of these nanoparticles, and then after reaction, it's almost indistinguishable. Here you see the two before and after reaction looks the same, and here you see the same. So copper-nitrogen functionality before the reaction as prepared, and then the formation of these copper-copper clusters. We can do analysis of this type of data, and we can really understand, as a function of the reaction time, how much is the percentage of the sites that remain as single atoms. In this case, we started with a highly dispersed catalyst. Everything was a single atom. And then under the reaction, as a function of the time, at this constant applied potential, we get to about 10 to 15% single atoms. The rest are nanoparticles. You can plot the coordination number of copper, and you can see that it increases, going to about 8 point something, and this is corresponding to small particles. From the coordination numbers in X-abs, you can get an idea about the particle size, and this will be about 1.3 nanometers. Why is important spectroscopy, and why is important operando spectroscopy? I cannot do these measurements under reaction conditions in an electrochemical cell, in a transmission electron microscope, or in any other microscope, because I'm looking at, I will need to have atomic resolution, and the observational probe, in this case the electron beam, shouldn't disturb my sample. And this doesn't happen. That means the only thing that I have is a spectroscopy. And the only thing that I have is a spectroscopy operando, because before and after, the system is reversible. So I think this is a very good example to show why do you need this operando characterization. So now that we know that our samples show this formation of nanoparticles and that there is this redispersion, so there is some dissolution and there is redispersion because copper likes to find these strong defective sites with the nitrogen coordination on the carbon. And now we decided to see we can play with the selectivity by applying different potential pulses. So we want to understand what happens during the potential pulses, and if we can tune how much we have in terms of small clusters, large particles, and single atoms. So we apply these potential pulses, always the same anodic potential, and always the same cathodic potential, where we are doing CO2 electroreduction. And here I'm changing just the length, how long am I staying during the cathodic pulse, where I'm doing CO2 electroreduction. And you can see the comparison I showed you before for the single atom catalyst and the just constant applied potential. I go from single atoms to about 10–15% of single atoms. The rest are nanoparticles. If I look and I apply these potential pulses with a long cathodic pulse, I can see these oscillations here. That is the way I'm tuning my potential pulses. I'm sintering my nanoparticles, and then I'm redispersing, sintering, redispersing. So these oscillations correspond to these cycles that I'm doing when I'm applying the potential pulses. Sorry. If I change the length of the cathodic pulse, I stay shorter at the cathodic pulse, and I go longer in this anodic pulse, I can see that still these oscillations, so sintering, redispersion, but I can see that at the end, I end up with much more of the species as single atoms. Instead of this 10–15%, I end up with maybe 50% as single atoms. So you can tune this under reaction conditions. And these are the distribution of the different species. I can show you also the coordination numbers as before. So under potentiostatic conditions, I get to a coordination number that corresponds to about 1.3 nanometers in particle size in average. Again, this is an average because this is ensemble averaging measurement. And if I go to shorter and shorter cathodic pulses, I can go to much smaller nanoparticles or clusters, and I can go to some other intermediate sizes. So what I try to illustrate with this is that I have a possibility of not only tuning the activity and the selectivity of this catalyst, I have a possibility now to understanding why is the selectivity changing? Why am I suddenly making with this supposedly single atom catalyst that I already showed you that this don't remain a single atom under operation, they start to make these small clusters and nanoparticles. And the fact that this structure is changing is helping me to change the selectivity. So if you apply short cathodic pulses, you get a larger fraction of cationic copper species, and you get smaller particle sizes. And very important, we achieve a dynamic control of the structure of this material. And something, we have some sessions about single atom catalysts. I always ask to be very cautious because maybe your single atom catalyst might be the precursor for the real active material during the reaction. And keep in mind that this process could be reversible. So now I can show you the summary of the results that we have for this part of my talk. So the selectivity is changing as I change the length of the cathodic pulse. This is how long am I doing CO2 electroreduction. And I'm making hydrogen at the beginning with the single atoms, which I don't want to make. And then if I go to longer cathodic pulses, I start to make other products. And this coincides with this change. I go from the single atom configuration to applying longer and longer cathodic pulses. I start making small clusters, then I make nanoparticles. And if I play with the length of the anodic pulse here, I can go back and start induce redispersion. So imagine I'm in the electrolyte. I have my nanoparticles, and my clusters are going to be oxidized and also are going to be hydroxylated. And so this is easier to redisperse when we start going into these conditions. And this is what we are doing here. So I'm changing the length of the anodic pulse, and I can redisperse and go back to this structure. And this is highly reversible, and we don't see a lot of material loss. So this goes, you have some copper going into the solution and then being redeposited. So I wanted to give you this example of the single atoms as the easiest thing to do, but I wanted also to illustrate that even a very nice, well-defined single crystal can be very complex. There is a lot of discussion in the literature about this CO2 electroreduction and whether there is a role of the particular structure of the material, in this case, the crystalline facet. And we show that we can make with the same single crystal, either 111 or 100, either mainly hydrogen. This is bad because in this reaction we wanted to make hydrocarbons and alcohols, or we can make hydrocarbons and alcohols. And it's exactly the same single crystal when you look at it locally. But when you look at the mesoscale, these two single crystals, in this case copper 111, one of them, the one that makes hydrogen, has very large terraces and only a few steps. And the one that is making the hydrocarbons has a lot of these steps. This is before reaction, this is after reaction, but this already shows you that even when you're looking at a single crystal, the history of this material, the step density that you have and the orientation of these steps is going to be changing every time that you do the reaction, even though we try to always regenerate it in vacuum with the normal methods, the sputter and annealing. It never regenerates to the original state. So this beautiful surface that the theorists can model very nicely is only making hydrogen. This more stepped surface, which is much harder to model, this is the one that is making the hydrocarbons. And it doesn't matter if you start with copper 111, with copper 100. We have done this also with copper 310. What matters is how many of these steps you are creating under reaction conditions, and most likely also which impurities are coming underneath your surface under reaction conditions that are going to help you to stabilize these strange step shapes. And this happens when you are putting these super clean single crystals in an electrochemical environment. So I wanted to show you that even, I mentioned at the beginning, my catalyst active sites might be created under reaction conditions. I might also destroy them under reaction conditions. And this is an example for a copper oxide cube catalyst. These are the initial catalysts. You see here a very nice, well-defined 100 facets. I put it in the electrolyte, and immediately I already see that some of these cubes break. I can see the formation of these small particles, and this is, you are seeing here as a function of time, a movie with transmission electron microscopy in the liquid environment. If you make the initial precatalyst smaller with different dispersion, you see at the beginning there is a lot of detachment, even just put it in the electrolyte. And now if I start my reaction, you can see here a lot of also mobility. You're going to see some of these nanoparticles are going to be getting together. You're going to see this detachment, some redeposition, some of them in this case is not being redeposited anymore. We just lose the material. And this matters because the selectivity is changing as the structure of my catalyst is changing. In this case, I wanted to make ethylene from these two types of catalysts. Ethylene is in red. This is reaction time from 0 to 12 hours. And this sample, where you see that I still keep some of these large cubes, but I also got a lot of nanoparticles, is much more stable in terms of the ethylene production as compared to this one here, in which very quickly I stop making C-C coupling and I start making more of the CO. So with this, I think I could illustrate why it matters that the catalyst, looking at the catalyst structure under reaction conditions, but I also wanted to talk about the absorbates, because this is a very complex reaction. If you are talking to theories, you want to try to understand what is on the surface while you are doing the catalysis. For this, copper is an ideal system because you can do surface-enhanced Raman spectroscopy. And you see here some images of our catalyst, this copper oxide catalyst, before the reaction. After the reaction, you see already the changes in the structure. And you see here the Raman data as a function of the applied potential. I'm plotting here two different configurations of CO on the surface, this stretching vibration and this frustrated rotation. And what we know now, working with our theory collaborator, Nuria Lopez in ICIQ in Tarragona, is that the ratio between these two absorption configurations is correlated with the CO coverage on the surface. And that the higher is the ratio between these two features, the higher CO coverage on the surface. At the same time, if you plot the intensity ratio of these two features related to the CO coverage as a function of the applied potential, this is in black, and you also plot the selectivity for the C-C coupling products, in this case ethylene and ethanol, there is a very nice correlation. So we can detect some intermediates on the surface, in this case, this absorbed CO. We can correlate this with the selectivity, but it's not so simple. Very recently, we have seen that it doesn't only matter how much is the CO coverage on the surface, it also matters what is the CO to OH coverage on the surface, especially when you are trying to get to oxygenates and, for example, ethanol. It's not so nice if we only are able to detect CO, because the reaction pathway and the different models that are possible are very strongly dependent on what can we detect. There are different pathways, there are different intermediates, and experimentally CO is the first step. So what else can we detect? So we spend a lot of time trying to create samples. In this case, these are copper surface, very rough, to get a very large surface-enhanced Raman signal. And you see here the products. We can make a significant amount of ethylene. We can make also ethanol. And ethylene production starts before the ethanol production. This is ethylene, this is ethanol. The Raman data can be distinguished when you are at the onset of ethylene production and when you are at the onset of ethanol production. You can see by eye that these two spectra look different. And so what we could do, working again with the group of Nuria Lopez in theory, was to try to assign our Raman features that we are seeing here, our Raman bands, with specific absorbates intermediates on the surface. And we see different ones when we have ethylene and we have ethanol. But what we learn is that there is a common first intermediate. And then, depending on what you have on the surface, you could go to ethylene or you can go to ethanol. So in more detail, if you calculate CO interaction with the surface, depending on what is the coordination of copper on the surface, you can see a very large difference in the Raman shift. Here is 7 to 8 coordinated copper, and here is 4 to 5 coordinated copper. We know from scanning tunneling microscopy in an electrochemical environment, we also know from atomic force microscopy in an electrochemical environment that my surface, even a single crystal, doesn't remain flat. You start to make small clusters, and you have highly dispersed species there, but it's changing, the surface is roughening. So while I'm doing the electrocatalysis, and certainly when I'm changing the applied potential, my surface is restructuring. And the Raman data actually also give you an indication that when you are making ethylene and when you are making ethanol, you see here these absorbates on the surface look different. So we have predominantly, when we are making ethylene, these absorbates, and when we are making ethanol, we still see this. And our hypothesis, based on the theoretical models and all the observations that we have from spectroscopy and also microscopy, is that my surface is complex. It has some highly coordinated sites that are going to make hydrogen. We might have some intermediate coordinated sites that help us to make ethylene, and then there are some strained, low coordinated sites, and ideally, if you have also some oxygen there, that are going to be favorable for making ethanol. And it's not one or the other, because these are changing depending on the applied potential, and these species are also changing as a function of the reaction time. So this is the model that we came up with our theory collaborators. We can detect experimentally with Raman this intermediate. We can detect this intermediate also with Raman experimentally. And this is the model that we propose, depending on the sites that you have on the surface, again, that are changing under reaction conditions. We can go through this pathway through ethylene, or we can open up this pathway here. In fact, if you dose some of these intermediates, you will get similar features in the Raman as when we get this directly from the CO2 dosing. So highly under-coordinated strain copper sites enable the reduction to this intermediate that opens the pathway for ethanol formation. So I have only a few minutes more, and I wanted to show you something because I believe that it's very important, this combination of a spectrum microscopy. So a different electrocatalytic reaction, same material system. Now I'm doing nitrate reduction reaction to ammonia. And we have now the possibility of putting these electrochemical cells in the liquid transmission electron microscope, and you can follow as a function of the reaction time for a given applied potential, how the catalyst is restructuring. But now I can go also and do the spectroscopy with transmission X-ray microscopy at the synchrotron, and then I can say what is the chemical state of which parts of my sample. So this pink data here correspond to the copper 2O, and this yellow here correspond to metallic copper. So I have some dissolution and I have redeposition, and this redeposition makes these small particles. Once we are making ammonia, we have the majority of our catalysts as these smaller particles that are metallic in the metallic state. And in the intermediate state, we are making this other product. So we can follow this, and again, my idea to show this data is to show you how important it is not only to look at ensemble averaging measurements, because my ensemble averaging measurement is not going to tell me whether different parts of my sample have different chemical state, different structure, and so combining this spectrum microscopy, I think, will be very important for catalytic understanding. Since I'm running out of time, I just want to give you some final thoughts about this idea of being able to restructure the catalyst under reaction conditions. And I started with these copper oxide cubes, and I told you that we could use them for CO2 electroreduction under potential static conditions. I gave you some hints what we can do by applying potential pulses in terms of the structure of the catalyst for the single atoms, and how does this change the selectivity. Now we can apply these potential pulses also to this copper oxide catalyst, and depending on the length of this anodic pulse and depending on the length of the cathodic pulse where I'm doing the CO2 electroreduction, I can tune the product selectivity. And there is regime where I can get a very large signal of ethanol formation. And this regime we can follow spectroscopically and with diffraction and find out what happens to the catalyst. So when you look at these materials at the synchrotron, you can follow with these applied potential pulses, how do we get the oxidation of this material? We can get copper 1 species, copper 2 species, and the X-rays, X-ray absorption spectroscopy, gives you ordered and disordered phases. This is important because sometimes the catalysis is not being done, most of the time it's not being done by the perfect crystalline phases. If you combine with XRD, you can learn also what is doing the crystalline component of your material. And in this case, for example, we can apply a potential pulse and we can measure the strain in the metallic copper phases. We can follow the formation of the oxidic copper phases. With all of this information combined, I can make a model in which if I have a metallic surface, not perfect, with defects, we will get this ethylene formation. If we have copper and copper 1 species and copper 2 species, highly disordered, combined to each other, we enhance this formation of ethanol. And if you start making a very thick copper oxide that you can make by applying these long anodic pulses going to the right applied potential, then we don't get ethylene anymore. We start making CO and methane. So having a copper oxide or a bulk copper oxide is not good for this reaction. With this, I get to my take-home messages. So I hope that I could show that you can create a model system that can be designed to reproduce important aspects of a performance catalyst. However, we only make pre-catalyst. The real catalyst is metastable. They will adapt to your reaction conditions. The pre-catalyst structure influences how this adaptation is going to happen in the operando transformation. So all the synthetic chemists working in catalysis, this is a very important component, but you need to understand that this is only the precursor material. This is not the real active material. The active state is formed during the catalysis, and the active sites are dynamic. So they will evolve during the reaction. This is why if you want to get mechanistic understanding, you need to be able to look at this material under realistic reaction conditions, which is many times a big challenge. Trace amounts of non-metals in metallic catalysts or metal impurities or metal oxides, they will determine the active sites' local environment, structure, and electronic properties. So if you are doing CO2 electroreduction and there is something under reaction conditions coming into your material, which we believe is happening in these single crystals, this is going to affect not just the structure, but also the electronic properties. And finally, the dynamics of the active sites must be coupled with kinetics of the reaction. So if you have suitable non-stationary conditions, as these pulses that I was showing you here, maybe you are able to overcome some of the limitations that you otherwise are going to have, and maybe you also can use this to tune the selectivity. I'm enjoying the wonderful weather here and this beautiful location, but I'm here presenting the work that this wonderful team of researchers is doing in my departments at the Fritz Haber Institute, and they deserve all the credit, and also the collaborators in different synchrotron facilities worldwide. Thank you very much. I will be happy to take questions.